Dear students, today we are going to discuss about special theory of relativity. This was propounded by Einstein in 1905 and it has two postulates. One is that the laws of physics remain invariant in all inertial frames. Now, I hope all of you understand that a frame of reference which is at rest or which possesses a uniform motion is called as an inertial frame of reference. So, we have two frames of reference S and S prime. This frame of reference S is at rest and the frame S prime is moving with respect to S with the velocity v, with a constant velocity v. Since this frame is at rest, its velocity is 0, consequently the acceleration is also 0. And since this frame of reference, inertial frame of reference, possesses a uniform motion, its velocity is constant. Consequently, the acceleration is again 0. So in such frames of reference, what do we say? We say that the Newtonian laws of motion hold good. And what do we mean by that? Is that the basic equation of Newtonian mechanics, that is force equal to mass into acceleration, holds good, or it retains its form. Retains its form. And how do we understand that further? Because these frames of reference are either at rest or they possess a uniform motion, consequent to which there is no acceleration associated with these kinds of frames. Therefore, there is no additional force which acts on the system or the object that we are intending to observe. Therefore, we don't have any equation of the sort F is equal to ma plus minus ma prime, where this acceleration would have been the acceleration of the frame of reference. But that acceleration does not exist, and Newtonian laws, they hold good. The equations don't modify. In such frames of reference, Einstein says that the laws of physics remain invariant, which means the results of an experiment are essentially the same whether we perform them in one inertial frame or in the other inertial frame. Now, the second postulate is that the velocity of light in vacuum is constant, independent of inertial frame source and observer. Well, that is a very thought-provoking postulate that makes every one of us very curious. What does that mean? Now, if we try to interpret this postulate, it essentially means this thing. Suppose a bus is moving or a train is moving with certain constant velocity v. So we hold it as an inertial frame of reference. Now, from one end of this train or bus, from one end we throw a torch, light, which obviously moves with velocity c, and this train or this bus is constantly moving with velocity v. Then for any observer who is watching this phenomenon from this spot, for him the velocity should be c plus v by the concept of relativity. Similarly, for an observer who is standing here and the torch is thrown from this side, the velocity is c, but the train or the bus is receding from the observer. For him, the velocity should be c minus v, but that's not the case. Experimentally, it is confirmed not once, not twice, but many a times that velocity of light essentially remains the same. So here it is c, here it is c. Now that's quite thought-provoking, but we will gradually land into it that how is it basically true. Now this postulate of special theory of relativity obviously has two important beautiful conclusions. One is length contraction, and another is time dilation. We know that all velocities are basically the ratio of two things. One is length and another is time. If velocity of light has to stay constant for all inertial frames in vacuum, that essentially means that length and time will have to change proportionately. If length contracts, time has to dilate. Now this length contraction implies that for an observer for which the object is moving, the lengths will appear smaller. But what does time dilation mean? I think I need to take an extra minute on making the students understand about time dilation, because somehow they are able to conceive the idea of length contraction, but they do commit serious mistakes while turning to this concept of time dilation. Look at it, what does it essentially mean? It means that, say, if length shortens, the time also has to have a smaller value, because they have to change proportionately to keep this factor constant. Similarly, if length has a large value, the time too has to have a large value so that they change proportionately to keep this factor constant. Now, we say that the outcome of this postulate is that length contracts. If length contracts, time has to dilate. What does that mean? Dilation of time means the count of time will be smaller. We will be counting lesser number of minutes, lesser number of hours, lesser number of minutes, or lesser number of hours. And how does that happen? That cannot happen unless a clock does not tick slowly. The clocks tick slowly. The watches, your clocks, they tick slowly when you are observing an object from an inertial reference frame which is moving with a velocity that nears the velocity of light, that approximates the velocity of light. So that's all. Length contracts, time has to dilate, and by time dilation, remember, I'm reiterating that time dilation means that clocks have to tick slower so that it takes larger time to complete 1 minute. It takes larger time to complete 1 hour. So the count of the minutes and hours is less. So that keeps the ratio L by T constant. So that is the second postulate. Of course, we will not mess up all the things together. We need to go into this one by one, the first postulate and then the second postulate. And we'll try to gradually build the idea, both in terms of a mathematical description and then a physical interpretation. And then this beautiful topic like spatial theory of relativity is never completed. It always lands you into further curiosities, but we'll try to gradually do it. We'll not do a mess of it. So from here we turn to the next page. Now, going back to the first postulate, that is, the laws of physics remain invariant in all inertial frames, and Newtonian mechanics holds good there. In addition to that, we have something called Galilean transformation. I hope all of you, as students of first semester, are aware of this. Galilean transformation. Galilean transformation is a set of equations that connects the description between two inertial frames of reference when they go to describe the same event. In all, it connects the coordinates of one inertial frame with another while observing a common event. So this inertial frame is S, this is S prime. The observer here is O, here it is O prime. The coordinates here are X dash, Y dash, Z dash. Here they are X, Y and Z. The time here will be denoted by T and here it will be denoted by T dash. The simplest equations that we know of are X dash is equal to X minus Vt. Y dash is equal to Y. Z dash is equal to Z and T dash is equal to T. That's it. When we choose these two inertial frames of reference to connect them in terms of Galilean transformation, remember, we assume that the motion of one reference frame with respect to another with a velocity v is only along x direction. The rest of the two axes, that is y and z, are parallel to each other. Therefore, the coordinates y dash and z dash will essentially be equal to y and z because these two axes are parallel to each other. The motion of this reference frame is only along x-axis. So we are describing the transformation like this: x dash is x minus vt, and that's quite obvious to realize. For example, if we have chosen a point here, so if I have chosen a point here, so I've chosen a point here, so its coordinates are x dash, y dash and z dash. So I connect it like this, and from here I connect it like this. From the point of view of this observer, its coordinate is x, and from here it is x dash. And since this inertial frame is moving with respect to this inertial frame with the velocity, constant velocity v, we know that this distance obviously will be vt. In a time t, this will cover a distance vt. Therefore, by triangle law of vectors, that's quite easy to analyze that vt plus this x dash is equal to x. So it's from here that we get a relation of this kind. The other 2 or 3 coordinates will essentially remain the same. We also assume that at the beginning, we have chosen to synchronize the time coordinates of the 2 inertial frames. At the beginning, t dash and t are equal to 0. So we have chosen to coincide the coordinates at that time, right? But now when we go to turn into the spatial theory of relativity, which even though we assume in inertial frames of reference, which even though we assume that Newtonian mechanics must hold good, but we see that these Galilean transformation equations, they prove to be inadequate in giving us any descriptions. So they prove inadequate. So they prove inadequate. I should use this word, inadequate. Galilean transformation equations prove inadequate in describing an event which is described by this spatial theory of relativity. Now, how do we understand that? Now, or shall we turn to next page for that purpose? See, if I again choose 2 inertial frames of reference, one is s and another is s prime, and s prime is moving with the velocity v constant with respect to s, and at this moment we choose to describe an event which moves with the velocity of light, or with a velocity that approximates a fraction of the velocity of light. So let us see how do the Galilean transformation equations fail. So suppose the event that we describe is a light signal itself. We have chosen a light signal itself, right? So what should happen if we use the distance formula? So from one reference frame, it should be x square plus y square plus z square is equal to r square. And we are trying to begin this light signal at the moment when we have synchronized the clocks of the 2 reference frames s and s prime. So when we begin to describe this event, when we begin to observe this event, what we have done essentially is that we have chosen to coincide O with O prime. So we have chosen the event a light signal that we are observing both from the perspective of s and s prime. Now, using the distance formula, simply the distance that this light should travel is essentially given by this formula. And of course, since light is moving with velocity c in certain time t, we can write x square plus y square plus z square minus c square t square is equal to 0. From the point of view of another observer, this should be x dash square plus y dash square plus z dash square minus c square t dash square is equal to 0. And if both the equations refer to the same event, because we believe that we have done a one-to-one correspondence between 2 reference frames while describing this event, then obviously this and this factor, they will cancel out when we equate these 2 equations, because again we assume that y and y dash are parallel, z and z dash are parallel, and we have chosen to synchronize the clocks of the 2 reference frames, so that way t and t dash are also identical. So we are essentially left with this x square minus c square t square will be equal to x dash square minus c square t dash square. So we can also cancel out this factor because t and t dash we assume that they are identical, which they are not, which we will prove in a while from now. Now if we use Galilean transformation equations for x, we have to write, so we will write x minus vt and it's visibly clear that left hand side is not equal to right hand side. Therefore, for describing the events which are moving with velocity of light, say the light signal itself, Galilean transformation equations prove inadequate even in an inertial frame of reference. Therefore, what we assume that we need to shift to some other kinds of equations that will suffice our needs, and those equations are called as Lorentz transformation equations. So we'll move to this. Now, before going to these kinds of equations, we also need to ponder upon that what changes essentially do we need to make these set of equations consistent with the observations of special theory of relativity. We need to think on that, ponder on that. What essentially do we need to do? We have chosen two reference frames, remember, in which the motion of one frame with respect to another is only along the x-axis. So, we have to relate one frame with respect to another not only in terms of x but also in terms of t. The other assumptions like, let's move to next page. See, the other assumptions like this kind of x minus vt, try to understand what I want to convey. So these were the Galilean transformation equations that were available with us as a convention, as a standard convention, but they have failed in terms of observing an event that is moving with velocity of light. So in order to make these equations consistent with the observations of special theory of relativity, we want to make certain changes. That is what we have arrived at. But we also need to think that what kind of changes can we make? Because we have chosen two inertial frames in which y and y dash, z and z dash are parallel, therefore let us assume that these two are essentially true. They are true, they are okay. This is also okay because we know that one reference frame is moving with respect to another only along x-axis. This also seems to be good. Then the only thing that we can ponder at is that maybe the time interval of observing these two events from the two reference frames is not identical. Therefore, all I mean to say that every x is to be related with x dash and t dash. Every t is to be related with x dash and t dash. And once we guess this, we are probably on the right track. So let us do those equations. Let us choose those equations. Therefore, we can choose to write that x is equal to ax dash plus bt dash. We can choose that t is equal to, suppose, some gx dash plus some ht dash. But again, I'm emphasizing that the primed coordinates x dash and t dash are the coordinates in the s prime frame of reference, and x and t are the coordinates in the s frame of reference, and both are inertial. Now, again using the equation that x bar is equal to x minus vt, if we have chosen to observe this event right from the beginning, when we have synchronized the clocks of the two reference frames, at that time obviously this x dash is 0, this is 0. So when x dash is 0, x is equal to vt. Let us see what do we get from that. So once x is vt, this is 0 and then it is bt dash. I'm using this equation in this and this. Now from this, t is equal to, x dash is again 0, ht dash. Then I can also choose to put this t here, so it will be v h t dash is equal to b t dash. T dash and t dash will go. We are essentially left with b is equal to v h, and that's a very important equation that's going to make the base of what we want to achieve. Now let us move to next page. Now again we'll go to the light signal that we are intending to observe as an event in these two reference frames. So again we'll write the equation that x square plus y square plus z square minus c square t square is equal to x dash square plus y dash square plus z dash square minus c square t dash square, right? Again, since we assume that y and z are parallel to y dash and z dash, so they will cancel out. So we'll write x square minus c square t square is equal to x dash square minus c square t square. And why are we equating these two equations? Remember, because we are describing the same event from the perspective of two observers from two inertial frames of reference. That is why we have equated them. I'm repeating things again and again because you are beginners in physics. So for x, we will substitute what we have just guessed in the previous page. So x will be ax dash plus bt dash square minus c square. T will be gx dash plus ht dash square. This is equal to x dash square minus c square t dash square. From here, what we can do very quickly is that we can choose to equate the coefficients of x dash square, t dash square, and if there is some other factor. We'll try to see that. Now, what are the coefficients of x dash square on this side? So it is a square from here. From here it is minus c square and g square. So this is equal to 1. So we have equated the coefficients of x dash square. Now what about the coefficients of t dash square? From this side it is minus c square on the right side, and on the left side it is b square from this term, and from this term it is minus c square h square. And then, because it is an a plus b whole square formula, there will also be a factor of twice a plus b. So we will have a factor of twice x dash, t dash, and inside we are left with a, b, right, minus c square g h. And because we don't have a term identical to this on the right side, the coefficient is 0. So I think we are quite near to the results. Now we will again substitute b equal to vh in this, and let us try to see what we get. So obviously from the third equation you get ab is equal to c square gh, and in this you substitute b is equal to vh. A is vh, c square gh. So h and h will go. What is this g? Essentially it is a v by c square. Now once you obtain this c, you can substitute it here. So what do you get? So you get a square minus c square. Just a minute, I'll try to do it. So it will be a square minus c square. For g square I will write this, that is a square v square by c4 is equal to 1. So from here, so is it minus c square? We'll write that here. So from here what do you get? If you take this a square common, right, you get 1 minus v square by c square is equal to 1. So a will be equal to 1 by under root 1 minus, so it will be 1 minus v square by c square. So we have obtained one of the factors. So once we have obtained a, obviously we can obtain g. So let me rub certain things. So from here we get g is equal to how much? Av by c square. So this is v by c square, and in the denominator you have 1 minus v square by c square. So you have obtained a, make a star over here, you have obtained g. Now we are left with b and h. Now you can use this equation, b square minus this. So what do you get from that? So we are making one common substitution in all equations, that is b is equal to vh, and that is benefiting us a lot. So for b again we will write vh, so it is v square h square minus c square h square is equal to minus c square. So if you take this h square as common, right? And inside I'm going to write c square minus b square to cancel out this minus sign. I hope you understand that. So after that, so from here you get that this h square is going to be c square by c square minus b square, right? And even after that, I need to move a bit here, move a bit left. So from here, I am proceeding to this. So h square, if we divide both sides, numerator and denominator, by v square, what do we get? We get it is 1 by 1 minus v square by c square, right? So we have divided by c square throughout, right? So we have divided by c square in the numerator and in the denominator. So I hope you understand it is 1, and here it is 1 minus v square by c square. And once the square goes on the right side, we are left with this only. Okay. So h is this. So once you have obtained h, we know b is equal to vh. So b is equal to v by this much. So you are done. We are done. So we have obtained the 4 constant that we had assumed: 1, 2, 3 and 4, right? Next, what you will do is that you will substitute all these 4 constants in the basic equations that we had assumed, and those equations were x is equal to ax prime plus bt prime, and t is equal to gx prime plus ht prime. You have obtained the value of all the 4 constants a, b and gh, and once you substitute, I will directly write the results. You get x is equal to x dash plus vt dash divided by 1 minus v square by c square, or inversely you can write that x dash vice versa, x dash is equal to x minus vt divided by 1 minus v square by c square. The other result that you will obtain is y dash is equal to y, that is understood, and z dash is equal to z. And you will also obtain that t is equal to, once you substitute the value of g and h, you will obtain t is equal to, so you will obtain t is equal to t dash plus vx dash by c square divided by 1 minus v square by c square. And when you invert that, what do you get? You get t dash is equal to t minus vx by c square whole divided by 1 minus v square by c square. And these 4 equations, 1, 2, 3 and 4, are called as Lorentz transformation equations. And these Lorentz transformation equations, in the next video, in the subsequent lectures, you will find that these prove the standard convention in describing the events that fall in the domain of special theory of relativity. So this set of equations is known as Lorentz transformation equations. And using these equations, we will be able to describe the 2 special conclusions of special theory of relativity. One is length contraction and another is time dilation. That we shall do in the subsequent video. That's all.